Okay, everybody, how's it going? Thanks for being here on time for the class today. Today, we're going to continue our discussion on structural mechanics and using finite element analysis to solve some of these problems. We'll hopefully have a chance to kind of go back in our mechanics and materials past and refresh some memories and also provide a little bit of additional insight into some of the topics that you've seen in, well, actually buckling would have been in design of mechanical components here, or maybe it was in mechanics and materials, depending on who was teaching it. And then fatigue was also in design of mechanical components. And hopefully we'll also be able to talk about vibration. If not, though, the assignment that is going to be due a week from today, is that right? Yes, a week from today, that will give you a chance to learn about vibration. The buckling is not so much in that assignment. So let's see here. Okay, yeah. There is a convergence checkpoint that is due. It's in a little while, but it's okay. Hold on, I'm looking. Okay, yeah, session. So yes, the lab on Thursday you will do the lab. On Tuesday, the other team will do the lab, and then a week from so you have quite a bit of time before the assignment on this particular topic is due. It's going to be on the 22nd. We're getting close to the end of the semester. All right, but yes, the convergence checkpoint is due on the 18th. Thank you. Just a note on the final project. You do have a 4-minute video or two 2-minute videos that I'd like you to put together as well. So in addition to the getting ANSYS to do what you want it to do part of the problem, you also have the opportunity to come up with a promotional video. So trying to think of a bigger picture, could be slightly humorous, okay, or slightly relevant, hopefully, to what you're intending to do. And then essentially a 2-minute live presentation that kind of goes through the technical aspects of what you do. Any questions on what is upcoming with assignments and various things for this class? Maybe the nice thing is that once again, we don't have, we have essentially one assignment, this lab/post lab, instead of a lab that they do at 4 p.m. And last semester, I actually had it still do the same day. So it's not nearly as bad as, well, I don't do, they're all good, but it won't be as time demanding as some of the other post labs, like the airflow, like the heated wire. And we're not using Fluent. So take that for what it's worth. We're still using ANSYS, but we're using structural mechanics. Okay. Any questions, thoughts? All right. So today we're going to discuss buckling, fatigue, and likely vibration. Okay. So we're going to go back to this geometry that we had previously in the last discussion that we had together, where we were thinking about what happens when you have a kind of a thinnish, sheetish, platish, barish structure that we're applying tension to. And we're able to do, some of the somewhat straightforward calculations for calculating, We're able to figure out the normal stress, okay? Able to figure out what the strain is. And we can do this analytically here, and we were able to show that we can do it in ANSYS. what we're going to discuss today is the same geometry, but essentially figuring out whether or not the structure will buckle for a given load that we apply. And let's go through some of the theory before we go to ANSYS. What do you remember about buckling? What were the kind of the names, just like the people that we talked about, or the names of the different methods, different criteria that we had for buckling? Anyone remember? Yes. Euler, okay. So you see that there, okay. And then the other name was Johnson, okay. And you see that name there as well. Okay, do you kind of what do you remember about these criteria and how they were similar, how they were different? What do you kind of remember? Yes, Bobby.
It's like a length to diameter ratio of force.
Okay. Yes. So there's something called the slenderness ratio. Okay. And that slenderness ratio, okay, can be described as equivalent length. So the LE here, we'll talk about this a little bit, but there's some type of equivalent length over rho. And rho is what we call the radius of gyration, and that is the square root of I over the cross-sectional area. Now, do you remember how to calculate I for like your rectangular cross-sections and your circular cross-sections? Okay, so what is the I for a rectangular cross-section?
pH over 12.
Good, right, so pH cubed over 12, all right, and anyone remember what it is for a circular cross-section with a radius or diameter? Bobby, you're like, you got it. Come on, Spencer, I see you're thinking. Anyone? So there's an R, right, or a D. Okay, and to what power should that be if we're doing to the fourth? Okay, so that's good. Okay, so let's say R to the fourth. What else is there? What coefficient then? For a circular cross section. Okay, so you say pi.
Over 32.
Ooh, very close. That would be for J.
Oh.
Okay, so J has to do with, kind of, that was the one we used for torsion, right? And it's also kind of the resistance to kind of spinning about an axis. Okay? So remember there was a trick to remember the difference between I and J? I alphabetically comes before J, which means I is less than J. So it's not 30, and it's not, so, okay, go ahead, Bobby, yes?
It's 64.
Well, it's pi d to the fourth over 64, yes. Or it's pi r to the fourth over 4. Okay? So that's usually the one that I use in mechanics materials. It's the pi r to the fourth over 4. And then J, which we use for torsion, that is the pi r to the fourth over, okay, or would be over 30. Okay, as for if you're doing D. So I guess maybe I should write some of that down, but for I, okay, we remember, for a circle with a radius, this was pi r to the fourth over 4. And for this section, we'd have our H and our B, and this was, okay? And the area, and so then you can figure out that row. Roughly, the slenderness ratio is giving you an idea, right, of how slender an object is. And the equivalent length, all right, do you remember little bits about the equivalent length for buckling? Any recollections? What was the equivalent length for buckling? What did it depend on? Huh? Okay, so yes, that's true. The equivalent length will depend on the length of whatever the object is that you're compressing. Okay, that's true. What else does it depend on? Okay, maybe something like this. Okay, so it also depends on the boundary conditions. So if you have a beam, okay, that is fixed at both ends, okay, that means I've got moment constraints at the ends, and also I've got the horizontal constraints, and I'm pushing down. Is that going to be harder or easier to buckle than, say, if I just have a beam that's sticking out and I'm just like using my finger on the top? If it's constrained on both ends, it will buckle. And I guess maybe we should go back and just talk about what is buckling. Okay, yeah, I like the facial expression with that too, Bobby. Okay, so that was good. That's right. So like you're pushing it together in one direction, but it flows out in an orthogonal direction. And when it comes to Euler, this is what we call elastic instability. Or I'd say but not in elastic instability. Okay. So it's not dependent. The buckling is not dependent on the yield strength of the material if it has a very high slenderness ratio. So if you're thinking of columns or something that are very narrow, have a high slenderness ratio, it's completely dependent on the elastic modulus and geometry. And that's an interesting bit about failure, because usually when we think about failure, we're talking about systems where we're exceeding a yield strength. Okay? But when it comes to buckling, that it can be independent of the yield strength of the material and dependent on the elastic modulus. But okay, and what? I don't know. Lost the thought. So coming back to this, the equivalent column length, buckling is going to be dependent on the length as well. All right, and since we're talking about a system that has an elastic instability where it flows out, okay, orthogonal to the direction I might be compressing, then how I hold it at the ends is going to make a difference. Okay? So if I'm trying to make sure that it doesn't bow out, with my constraints laterally and momentumly, I guess that's not even a word, right? But with its moment, then it's going to be harder to buckle. So the equivalent length is this metric where essentially, okay, we say we have an LE, which is the equivalent length. Okay. And this is going to be equal to some, let's say, K value here, all right, times the actual length. So I could have a beam that is pinned. Okay, so pin. So it's constraining. You can see the keys. You have translation fixed, but rotation is free at either end. The equivalent length is just equal to the length there. Okay, so it has pins on either side, and I push. Comes out, right? If we have a system that cannot rotate but has translation free, and at the bottom it's fixed, that's also having an equivalent length of 1. Now, they have these recommended design values, okay? And so that's kind of like putting in little bit of a safety factor to avoid buckling as well, in some cases. Or in this case, they just say, if you're really going to do it like that, go ahead and just leave it at a value of 2. Okay? But typically, these design values are a little bit higher. And not in this case either, I guess. These theoretical values are usually based on, well, they're based on the Euler buckling criteria, and they're going to be used for both the high slenderness ratios and the lower slenderness ratios. So let's say that we have a very narrow, high, tall column, right? And now I make it really, really like a pancake fat. Okay? Do you think I even need to care about buckling? Is that even an issue? Well, no, right? That's like the old fashioned, maybe not old fashioned, but it's just as if we're doing a bar under compression. We don't have to worry about buckling. And of course, we can have a long beam or a long column that we're concerned about, and if I'm putting the pulling attention, it's not going to buckle there either. Okay? It's really just the compression. What happens in the in-between realm? So you're not really that slender, and you're not really that pancakey, and you have compression. That's where, which criterion do we use? Anyone in quadrant 2? So if you have an intermediate slenderness ratio, which criteria do you think we should use? Quadrant 3? Yes, quadrant 2, I see yes. Intermediate slenderness ratio? We were talking about it a minute ago. Yes, we want to use the Johnson problem, okay? So how do you figure out whether or not you're slender enough for Euler or you're kind of stubby enough for Johnson? Well, this may not look familiar because it's not often put in a textbook, okay? This curve, or maybe not, it is, the equations are put in the textbook, but actually Juvenile's textbook, I think it's a little less clear. Maybe, well, I don't know. It's presented a slightly different way. Which one of these is Euler? Well, according to the legend, and I just did this in MATLAB this morning, okay? So this is Euler, this blue, all right? And this is Johnson, here, the red, okay, or the dash dot, or whatever it is, dash it, okay. Given what we just talked about, what do you all think? Where would you use Johnson, and where would you use Euler? Like, over what regimes? There's either two curves, okay. Where do they apply? Sure, Bobby.
Oh, we use Johnson probably until they touch.
That's right. So, well, until they touch. So, are you saying coming from the left to the right? Right. So, you use Johnson. You're absolutely right. Okay. You would use Johnson until about here. Okay. And then you would use Euler over here. Now, this is called the tangent point. Okay, does anyone remember this? Okay. And I've included some equations there. So this is the x-coordinate. We can put that's a tangent. So this is like the horizontal component for the tangent point. And this is going to be the vertical component. Okay. So before I said Euler doesn't really care about the yield strength. Johnson very much does, though. Okay? So the Euler criterion, if we go back, this is the Euler equation. It says that the critical stress or unit load is going to be equal to some P critical. So P critical is a force divided by area, and it's pi squared E over the slenderness ratio squared. Okay. And if you plot it on a log-log scale, what you see is that it's a straight line, and it has slope of. Anyone know how to talk about slopes on log-log? What would I say the slope is here? Yes, I see that. I want a number. Anyone? What's the slope? This is a log-log plot. And if some of you have taken system dynamics and dynamic systems and control, DSC, you've done some Bode plots. Maybe not many people have taken them in that class yet. How do you describe the slope? You can think back to your SN curves as well, if you like. So in this case, we're describing a slope that's essentially not in terms of a linear scale, but it's in terms of decades of decay or decades of growth over decades of, and decades means power of 10, okay, the slenderness ratio. So if I go 1 decade to the right on this graph, how many decades do I go down? 2, right? So the rise over run, who said that? Yes, thank you. Thank you, Matt. So the rise over the run here, right, is, what was that? No. Oh, no. We're good. We're good? Did I call you the right name?
No, you called me right.
Okay, all right. I thought maybe I called you the wrong name. Yes. Okay. So yeah, we're going down 2 and we're going over 1, right? So it's -2. Okay. So the slope here is -2. Okay, and that's what you see represented here. This is just another way to write essentially mx, well, in this case it's b minus or b plus mx. Now, sorry, that's not exact. Let's just do it a little bit better. Here we go. We can do it like this. -2, 1. And you're like, that's not right. -2 looks shorter than 1, right? Why is that? Because it's not a square grid. And it's not the aspect ratio of the grid has been altered slightly. Okay. All right. So if you're to the left of this critical tangent point, so this is what we call the tangent point, okay, and we said, okay, it's got this equation, square root of 2 pi squared ESY, or E 2 pi, all right, so this is at the square root of 2 pi squared E over SY, and then this comma, and this one's actually easier to remember, it's just the yield strength over 2. So you see the yield strength of this material is 500 megapascals. This is happening at about 250, or it's happening at exactly, well, according to this, exactly 250. My circle may not be in the exact right spot, but it is 250 megapascals. Okay, so what's cool is that the Johnson parabola captures maybe something that's kind of obvious. If it's a pancake, right, then it should just yield this critical yield strength. It's just going to be what you expect. Okay, it's 500 megapascals. But as you get more slender and slender, then some elasticity the elastic instability can creep in, and it's going to fail not only because of the yield strength, but also because it can bow out. Right? So you would use this. You ignore this part here, because that's Euler, right? But then Euler is good once you get to high slenderness ratios, and so you ignore this part of Johnson. Okay, and so this is the curve, right? And that curve, sometimes it's like, oh, okay, that's like a critical thing. So you start to think, well, when am I safe from buckling? It's when we're under the curve, right? If you're above the curve, that's when you will buckle. If you're below the curve, that's when you will. Now, in ANSYS, very much, we're only going to show you how to do Euler buckling, okay? Because it's solving this elastic instability problem. Maybe it does do Johnson, but I haven't to be honest, gone into it to see if I can make it do Johnson, right? Nonetheless, if you have these beams or these different structures, you can have you have a tool that, with some assisted analysis, can help you make good decisions. All right. So let's go ahead and let's see if we can get this geometry into ANSYS and see if we can do a buckling problem. So here we're going to apply. Well, let's go ahead and get. Well, I'll describe it because we've got to get workbench going. Okay. Here, what we're doing is compressing the plate with 10 kilonewtons. Right, that's quite a bit. And in our analysis, we need to put the appropriate material properties. And we're also going to essentially see, okay, does this force that we're applying, is it above or below the critical force that you would have for buckling? All right. So we'll go ahead and we're going to actually kind of repeat what we did before. We're going to do static structural, and we're going to put in the engineering parameters, okay, that we want. We'll call it generic steel. We can right click here when we do it, and we'll make this the default solid material, so I don't accidentally not include that. We can put in density, which is 7850 kilograms per meter cubed. We can put in the isotropic elasticity, and here we'll say it's 200 gigapascals. We'll say Poisson ratio of 0.3. Later we will, I guess we can put it in, but later we'll put in an SN curve for fatigue. So, well, maybe we'll just do it right now. This value, oops. Okay. If we do a fatigue problem, okay, we're going to use 250 megapascals and 450 megapascals for the two values. I'll go through that later if we have time. Hopefully we have time. Okay, so here you can go to tabular. Oops. Okay, and we can do log interpolation. Here what you have is at 1,000 cycles, okay, the stress that we're going to have is the SF, that's the 450 megapascals, so 450 e to the 6, and at 1,000,000 cycles, okay, that's where we're going to have the 250, and we'll explain that in a little bit. Okay, so we're just putting the material properties in. We're going to go ahead and go back to the project, and we'll use space claim for the geometry. We will do 3D geometry, so we can leave that like it is, and we'll do new space claim. For this problem, again, the thickness is going to be 5 millimeters or half a centimeter, and the span will be 3 centimeters, and the length will be 15 centimeters. Okay, so here's our space claim. We click on Z, we click on this select here, we can do that. We'll go ahead and we'll put in our rectangle, and we click once here, we move out, hands off, we'll say we have 150 millimeters, hit tab, and we'll say that we have 30 millimeters, and we can hit enter. We do hit end sketch editing. We can rotate slightly. We can make sure that pool is selected. We click on this and we pull a little bit without lifting our left or the left button on the mouse. Then we hit 5, enter, and we should be done. That's the end of the geometry. And we close. Okay, now in Workbench, we can go ahead and double click on the modeling. And that, I guess, in space claim, it was already set to be using units of millimeters, so that's convenient for our problem. If you're doing different scaled geometries, then you want to make sure you change those units. What's nice, again, with structural mechanics and ANSYS is that you can do the meshing and the loading and the constraints and the simulations all right here. So we're waiting for the geometry to appear. While this is happening, I will test my, let's see, actually, yeah, let's do it this way. We're going to open MATLAB. I'm testing my computer now. Not kicking in when it's down, hopefully, but we will use a little bit of a script here when we do our buckling. Okay, so this one over here, good. Okay, it's in place. Great. Okay, the modeler or structural mechanics, good. Done there as well. Okay, so it's not bad to make sure that there's only, whoops, it's still thinking. Okay, it's not bad to kind of make sure there's only one solid in here. The materials, we're using our generic steel, and it has been assigned, all right, to this, to one body, and that's all we have. And we also have this nice SN curve, which we'll hopefully get to talking about a little bit later. For the mesh, we can come over here and we can, yes, you can add like a sizing, or you can come over here and change the, we don't want the, sorry, not this sizing. Right here, actually, under defaults, the element size, okay? So if we did like 5 millimeters, I think that's too large, as we've shown previously. Yeah, it only has one element through the thickness, and it's a little bit, it's just, we can do better. So if we go down to 2 millimeters, hit generate. Okay, so that looks like something that's a little more discretized. Here, what we'll do is go ahead and apply the compressive load as we're doing a statics problem. So we're not even doing buckling yet. We're just loading it statically. So we'll go ahead and we'll put a fixed n on the left side. Fixed here. Okay, apply. Okay, so it's fixed. And then on the right side, we need to apply a force. Okay, and we'll click that. You hit apply. And we can break it into its components. And if we're trying to put this in compression, which direction are we going to be applying it? Yeah, in the minus x, right? Yes, Federico.
Remember you went over this last time. This is if you're trying to like simulate a beam, like you need to have something in the mesh which is fixed.
Correct.
Right now. But at this point it's fixed and you have compression this way. But is it the same thing as having actually it would have like there would be a reaction force on this side.
Yes.
Like ANSYS would know that.
Yeah. So it's got the whole wall on this side. Okay, looking at it this way, right? This wall over here on this side is fixed, and I'm compressing it this way. Right? So so I mean that's essentially what we've got here, right? This is compressed, okay, and then this actually over here. Actually, I haven't specified the minus x yet. So now I'll put. And we said it was 10,000. That's quite a bit of 10,000 newtons, right? That's not an insignificant load. So 10 e to the 3. If I just do that, though, that's going to be positive, right? So instead, I need to do negative, like this, right? Because if I'm interested in buckling. For the solution, we can go ahead and insert some. Sure, deformation's always fun. We can put in some stress. Why not? We can do a normal. That's fine. Or we could do an equivalent as well. All right. We have different opportunities here. Okay, and we should be ready to go. So we hit solve. And we wait. What is the value that we should be getting? Well, if we come back here, this should just be negative, okay? Because it's in compression now, so it's just negative 67 megapascals, or negative 66.6. Repeating. So what do we have here? We put a probe, and we have, like we were saying, we have the 66. That's the right value. Okay. And we have this Poisson effect as well, right? In this case, if I'm compressing, it's going to be expanding in the other two directions. We're pretty good. We're pretty good to go here. Now, what do we do to do a buckling analysis? Well, there are kind of multiple ways to do this. The way we're going to attempt to do it. Oops. Okay. Here, we're going to close this, and then we're going to go into Workbench, and we're going to do eigenvalue buckling off of the solution, okay, of our static structural. And isn't that nice? It brings in all that stuff that we just did, and allows us to bring it automatically into a new model. So we'll now double click on this model. Is it working? Oh, maybe the setup. Sorry, we'll double click on the setup, and it's starting mechanical. And we'll see that it's added this eigenvalue buckling analysis. Okay. Now, with is it ready? Okay. Good. Okay, like this. All right. So you see, it still has the fixed support. It still has the compressive force, right? And now it has this this eigenvalue buckling analysis, right? And it's raring to go. Okay. It can just go ahead and I can hit solve. And what's interesting with this eigenvalue buckling analysis, and this is maybe when you take vibration, you'll talk a little bit more about this, or if you take vibrations, you'll have modes that this eigenvalue analysis illuminates. Right? And on this kind of, again, impressionist perspective, what we're saying is that as you compress, yes, there is this one mode, right, where you have essentially this top piece that kind of springs out, okay, or side piece, if you turn it this way, it like springs out this way, springs out this way, okay, and that would be one mode. You could also have, when you're pushing down, you could also have it push out sideways. That would be another mode, okay. So now, let's see. It has good. Those numbers look good. But let's go ahead and let's insert some deformation, so we have a little bit better idea. We can just retrieve the analysis. We don't have to run it again. We just retrieve this result. Okay, and so now we can kind of see what's happening. All right, this, and it's been auto scaled by 7 and 7.7, so it's a little more dramatic. You see, this was the fixed end down here, and this was where we were applying the compressive force. And so this mode of analysis, or this mode of buckling, is one that essentially has it going like that. The second mode of analysis, all right, if we retrieve this result, is a little bit different. You see, in this case, and you see it has to have zero slope coming out at the bottom because that's a fixed support. Okay. But the top has that force being applied, but it doesn't have that zero. Okay? It doesn't have that. It doesn't have to have that zero angle, and so this thing buckles out like that. All right. So this is mode. You could call it mode 2 if you like, and that's what it's called here. All right. Now, how do you know whether or not you're going to fail? Okay. How do you know if you're going to fail or not? Well, let's just go back to this one, retrieve this result. You see over here, there are these things called the load multiplier. The load multiplier is one that says whatever the magnitude of the loads that you apply, if you apply the load multiplier times that, that's when you would have buckling. Okay? So what we're saying, remember we applied a 10 kilonewton force to compress this thing. And it says buckling will happen at 0.69 times that 10 kilonewtons. That's when buckling is going to occur. Okay? So we're kind of done. We're pseudo done. We're kind of done. All right. And to get to the second mode, we would have to multiply by 6. All right. So at 60 kilonewtons, you could get this second mode. It's kind of a moot point, though. Right? You will have already failed by mode 1 with this 10 kilonewtons, right? So you gotta it will just simulate things. It will tell you interesting ideas. It will give you this information, but it's not. It's creating a pretty picture. We have to use some of our intuition. Now let's go a little bit deeper with this mode 1. And what do I mean by that? Let's go to MATLAB, okay? In MATLAB, all right, we've placed our elastic modulus. Okay, so this is just an analytical calculation. All right, and what we just spent like 15 minutes discussing Euler and Johnson. Okay, so the P critical here, this P sub CR, this is the force. Okay? According to what we just calculated in ANSYS, this P critical should be what value? At what value, at what applied compressive force do we have buckling occurring according to ANSYS? Huh? Yeah, it's 0.69 times the force. Thank you. Your name is? Juan. Okay, so that would have been 6.9 kilonewtons. Okay, because we applied a compressive load of 10 kilonewtons. So let's see what our analysis from DMC or from whatever course you've taken buckling, you've learned buckling. Let's see what it says. So we have our length of 15 centimeters, our span of 3 centimeters, and our height of 5 millimeters. The I, that's the BH cubed over 12 that we love. The area is the B times the H. The rho is the square root of I over A. These are all things that we just discussed. There's the rho, all right? And so let's go back. What is the equivalent length? So this, we need to look at another piece of information, right? This. Okay, so which scenario describes what we've just applied to this beam? Yes, the equal?
The second to right one.
Second to right. Okay, so you're saying this one? Okay.
Actually, no.
So yeah, I mean, we can, the equivalent length, all right, what we have is, yeah, okay, so you could, this mode is, yeah, let's go with this one, all right? Let's just go with this one for now, okay? But it could be another one. All right, let's see what happens. Okay. So let's say it's 2. Okay. We hit Control Enter. All right. You're right on the money. All right. Look, the P critical. What does it say? Yeah, that's right. Okay. So even though I had my 0.7 in there, and I was confusing myself. You're right. That is. Now, why was 0.7 in there before? Any idea? What?
0.707.
Yeah. Why was the 0.707 in there before?
Just can't help but realize it's root 2 over 2.
Right. That's true. That's true. You can't help but realize, and it's because the last time I did this example, I used a different case, or I showed what I'm going to show you now. Let's look at this 0.7 case. This 0.7 case, okay, and other charts will say 0.707. This chart just says 0.7. Okay. Another case would be you still have rotation at the end, but you have no translation. Okay, you see that? It says rotation free and translation fixed. How can I make ANSYS run that calculation? How can I tell ANSYS to do Yes.
Would you fix like on the top and bottom line instead of the whole thing?
Okay. Yeah. Okay. So that's so you're saying you could fix like this whole face or something
You know, like on the right side.
on the right side.
Yeah, that face. Could you fix the top and bottom to fix that side but at an axis?
Good. Good. This is the right again. So fixed and ansys has a specific meaning. It means it constrains all 6 degrees of freedom. Okay. So fixed will mean that all translations and 3 translation degrees of freedom and the 3 rotation degrees of freedom are out. This still has rotation. So we don't want to use fixed, but we can constrain displacement. Okay? So that will still give us the rotation on the end. So to do that, I'm going to come and add a displacement constraint to this face. Let's see, which one? This one, this face. Okay, and which directions do I need to constrain in terms of displacement? Yes, Olivia? Yeah, so Z is 1 and yeah, Z and Y. Good. Right, Olivia. So we're going to say free X is still free, but we're going to say that there's 0 displacement in the Y and the Z. All right? And so now we can run this simulation again. We solve. Uh-oh, maybe it didn't like this. Okay, so let's see, let's solve that one first. Invalid geometry. Fix the port here. Oh, it didn't. Right. Apply, all right. Now we can go ahead and we can solve. Okay, oh, and then we have to solve here as well. Okay. And so this value, so this loading factor, okay, is it going to be higher or lower than what we had before? Now that we've added these extra constraints. Is it going to be harder to buckle or easier to buckle?
Easier?
The other one. Yeah. Oh, right. So we've added additional constraints to this displacement up here, right? So now it can't do this, right? And you remember that there was that second mode where it was kind of still not moving left, right, but it was like kind of bowing out. Had that rotation on the top. So what we expect here is, at least for the first mode, we've made it more difficult to buckle, which if we did this right, we'll have a load multiplier that's higher. So now the load multiplier, before remember it was 0.691, now the load multiplier is 5.6, which means for that 10 kilonewton load that we're using to apply the compression, it's actually going to require 56 kilonewtons. Yes?
Just a quick question, what is the second mode?
The second mode represents this hypothetical, and it's more clear in vibration, I think. Remember, like if you have a string and you start vibrating it at a particular frequency, right? And it like goes up and down, up and down, up and down, right? That's like your mode 1. Okay? But then you remember, like if I double the frequency, I can start to put extra waves in it. All right? That's essentially what's happening when it does the eigenvalue analysis. Good question. All right, so let's see now. If we come back to this value, and it's a good thing we're using your brains, all right, collectively here, because you said, oh, that equivalent length is 2, right? And that's based on the chart. The equivalent length here now, according to the chart, should be 0.7. Okay, and this is the geometry that we should see. Actually, so let's go back to ANSYS. we'll just keep building the suspense. If we look at the deformation, do you see? That kind of looks like that mode, right? That's being described in our analytical expressions. So we'll put in the 0.7. Where is it? Here, 0.7 here. And we run it. And voila, look at that. 56 about. 56 kilometers. All right. So this is happiness. All right? This is happiness. ANSYS and Euler agree with each other. Isn't that beautiful? Now, what about Johnson? Okay. What about Johnson, right? So ANSYS can't really tell us what's going on with Johnson. All right. If we look here, okay, we got a few more calculations, all right, and we can figure out what the slenderness ratio would have to be. So in this case, the slenderness ratio that we've calculated for this geometry with this equivalent length of 0.7, the slenderness ratio is 72. Right? And the tangent slenderness ratio that is necessary is almost 200. Okay. So actually, for this system, right, if we look at the, whoops, not that, look at this graph, okay, the slenderness ratio is to the left of the tangent point for that system. And so even though it comes out really well, you would want to use the tangent. You would want to use the Johnson formula, okay? If we go back and we say when we had 2 for the effective length, like this, all right? Then, in that scenario, the one that we ran, the penultimate scenario, then you see the slenderness ratio of our system is actually above 200, and it's to the right of that critical slenderness ratio, or the tangent slenderness ratio, and so we would be fine using it. So, even though, right, it looks like Johnson, Euler, the software agrees, all right, it's still important to kind of know, okay, is this a Johnson or is this a Euler scenario? Okay, just from our analysis of our times in the past. Experiment always wins, right? So you're probably, as you get more and more advanced, right, and you get experience, so like, let's say that you're working for company XYZ, and you've been making these things, and you've got the simulations, you've got a general idea, like, okay, even though this is like a slightly high number, or I've done this analysis to get in ANSYS or in your finite element to get my numbers to agree, then you're able to say, okay, yeah, I can trust my analysis, I don't have to do an experiment. But if you've never made it, if you've never run an experiment, right, on a scenario before, people are probably not going to trust you completely, all right? So you're going to have, at least if you're doing the simulation, you're doing these calculations, you're trying to show people, this is what I think is going to happen. You've got to run an experiment, or you've got to have something in the literature around truth that verifies that, okay, your simulation is probably valid. Any questions on this? All right, so this is buckling. Now we've got a few minutes left. Okay, let's talk about fatigue. How would you think of what is your working idea of what fatigue is? What is your when you think fatigue, you think of how to model it? What do you think? Yes, Lydia.
Conditions that make your object deform forward or like tilted.
Okay, Yeah, so yeah, that's good, right? So you're saying, okay, you have some type of plastic result that happens at values, loading values or stresses that are below, let's say, the ultimate tensile strength for sure, and perhaps even below the yield strength. Okay, and how is that happening? What is the mechanism, or what is the loading like for fatigue? Yes, Bobby.
Mini cracks and big cracks.
Right. So yes, you have these mini cracks, and I guess the answer I was fishing for is that this is cyclic loading, right? So you have it going back and forth, opening, 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 and I didn't say the word closing because I mean closing has to happen too, but under compression you don't have as much growth of the crack. The crack is going to grow more in the tension, right? But it's a combination. It's opening. You have to have opening. Okay. And there are different modes, right? And there's like if you look at a crack, okay, people have like this, all these like slip-line fracture mechanics and these different ideas of what's happening. This plastic zone. This is an Irwin model in the upper right, and it's a big deal, right? It's a big deal. And when I have a chance to teach DMC, we talk about this Aloha flight 243 that had a significant failure. All right, and luckily most of the passengers were fine. Okay, but still catastrophic. Like a portion of the fuselage just came off, and it makes you think, oh, would you rather be? And of course, if you have proper inspection, everything's gonna be safe. So let me not scare anyone, right? Do you think you have? So let's not be too subjective. Let's be a little more objective here. Do you think that it's more important, or that's also subjective? Do you think the need for inspection is greater with planes that make lots of short hops and flights, or less with planes that make lots of short hops and flights versus planes that like just go longer distance and don't do as many landings and takeoffs? Yes.
For short hop flights would be more
Right. Okay. Why is that?
takeoff and landing adds more stresses to the structure.
Yeah. What is the load on a plane that you're getting that's fatigue based here? When I say takeoff and landing, yes, Frank.
But the inside is pressurized, so when it goes up in the atmosphere where there's less pressure, the fuselage wants to expand.
Right. Right. I mean, you can say, oh, the landing gear. I'm not talking about landing gear here. I'm talking about the fuselage, right? Yeah, of course, the landing gear is also going to be like experiencing more loading and stuff, so that's a different thing altogether. But the fuselage itself, yeah, it's going to be expanding and contracting every time you take off and you land. Okay. So in the Aloha case, it was a failure of the fuselage, and there was fatigue, okay, because of all the takeoffs and landings. All right. So do you remember these curves? SN. Okay. So this is, I guess, a comparison between steel and aluminum. Right? You remember that you have the knee, all right, where this thing goes kind of from slanted to horizontal. This endurance limit, do you remember what this was called? This is what we will call like the SN, or depending on geometry, will be SN prime or SN. Okay. And right here, right, we call this like the SF, or this is the low cycle fatigue limit. This was 10 to the third. Well, in this case, actually, I guess this is 10 to the fourth. So it'd be up here somewhere. Okay, continue to go up here. Okay, so this is the SF, 10 to the third. Okay, cycle limit. Low cycle fatigue limit. Right, and we've talked about this, well, maybe, I don't know, you've talked about it, I'm sure, at some point. Low cycle fatigue, right? that's more detrimental than high cycle. High cycle fatigue means, hey, it works for lots of cycles, which means you're below the endurance limit. Whereas if you're in this regime, all right, if you're under this part, or if better said, if your loads are in this triangle, all right, watch out. Okay. All right. The idea is that, at least for steels, and aluminum you can see has a slightly different behavior. For steels, if you're below the endurance limit, then everything is awesome. You should have 1,000,000 cycles plus. But if you are in this kind of Bermuda Triangle regime, that is when you're going to have something different. And there's actually quite a bit of variability here. Okay, and in the tutorial, we'll talk about that. Okay, we'll talk about that some. Okay, so with your experience in DMC, right? You had the endurance limit, that's SN prime, okay, and then you had the actual kind of infinite life here that we would have, and then a bunch of loading factors, okay, that went in, like the coefficients, okay, that you would have, and that could knock down the endurance limit to be a different value of SN. Okay. So, how do we go about running this type of situation, okay, in ANSYS? Well, we can plug in those components, which we already did for the SN curve, and have ANSYS predict based on the normal stresses that are involved, or the Tresca, or the equivalent of Malmese stresses involved, okay, whether or not we're going to have failure after a certain number of cycles, or how many cycles will we last with these different loadings. Okay. Now, analytically, right, you can figure this out. And I won't go through this right now, but do you remember how to figure this out? We were just doing logarithms, right, and log scale plots log plots a few minutes ago, right? And there's different slopes. You can solve, if you're under here, everything's awesome, infinite life. But if you're over here somewhere where the load is up in this region, then you got to figure out where you hit this line. Okay? And what you'll see is that as you move left or right just a little bit, there's a huge variation in the life that you have. Like just a few percent change in your applied load, your stresses that you're applying, can have a very large change, the factor of 10 change in the number of cycles you're going to be enduring. So that's another reason why you don't want to be operating in this regime. It's hard to predict. So let's go ahead and see. Let's see. We have a few minutes. If we can run a quick fatigue example. And then you'll do vibration in the assignment. That is thinking very carefully. So what we're going to do here is, okay. All right. Is it everything's awesome? Okay. So. Okay, this is what I'm looking for. Duplicate. Okay, thinking. Great. Okay, and then here in the model or the setup, what we're going to do is change it so that it's beam bending. All right, so if you look here, the geometry that we're interested in analyzing is going to be experiencing this cyclic load, okay, in the vertical direction. Okay, so we'll go, and it's going to be a value of 300 newtons. Okay. So here, what we'll do is we'll get rid of this displacement constraint, and for the force, we'll change the direction so that it's in the positive z. So we're going to get rid of this, and we're going to put it in the z direction, just like that. Okay, and we can solve this. Okay, and if we look, we have now a beam bending problem. Okay, and we can see, I'm not sure. Okay, the deformation, it's not coming out there, but the stresses are coming out. Not quite sure why that is having trouble here. Okay, well, but let's go ahead and we're going to add an analysis. Okay, and in this case, sorry. Okay, we can add fatigue, and we can add this fatigue tool. Okay, just like this. And this fatigue tool it's giving you the type. All right. So remember, you have different good midlines and various things where you can have like an offset, right, and you can oscillate about some value. Okay. And we're going to go ahead and leave it as fully reversed, okay? And we're going to look at the life, all right, of this system. So here we can go ahead and click. We can retrieve the result, or no, we have to evaluate. Okay, so we have to evaluate. Okay, and what do we see here? All right, we see this is telling us life. All right. And this is telling us how many cycles this endures, or how many cycles these different parts will endure. Now, so that means that out here, you see this is blue? This is 1e to the 6th. This is a million out here. Okay? But the bending stresses are higher as you get closer to the fixed region. Okay? And so the life, the number of cycles you can get, all right, could be as low as 10,000 or 9,000 right here. It says 9,006 in this region. Okay. Now, so we can figure out how many cycles we're going to go, okay, based on this fatigue analysis. Now, how do we do this? Well, remember that earlier we put in the SN coordinates. All right, and so if we do our analysis, okay, what we can see here is that our 300 newtons, okay, is the force that's being applied. The maximum stress, the normal stress, is going to be 360 megapascals. Okay, the SN curve that we're using has 250 for we're above the, you see that we're above the endurance limit. The 360 is above the endurance limit. So we know that the structure is going to be experiencing stresses that are above the endurance limit, so we cannot expect infinite life for this structure. And if you do this whole analysis, what you see is that we predict, okay, that we'll be able to have 13,000 or 14,000 cycles. And if you come over here, there's some minimum that we can't see that's around 10,000, 9,000, right? But this region over here, some of this, 15,000, if I put the probe over here, right? Let's see, 37,000, then it goes on to 9,000, right? And there's a lot of variability, like we said, 15,000, right? That node will last, it's predicted to last 15,000 cycles. So our analytical solution and this fatigue tool and ANSYS are actually in pretty good agreement. You're like, oh, but they're 1,000 off. Well, yeah, but there's a whole lot of variability when you're dealing with fatigue. What this tool is really telling you is that's where the problem is. The problem is at this base. You need to do something here. You either need to reduce the load, okay, or you need to change the geometry, thicken it or something, so that if you're striving for infinite life, right, you can get everything to be 1e to the 6, right, in a million cycles, so that everything is blue. Any questions on this? So it's another tool that you can use, but you have to use it with some caution, right, and an appropriate model. Well, that's all for today. What we've covered is not vibration. All right, so I guess you don't want to necessarily highlight what you haven't covered, but you'll in the video for the lab you'll be able to get some insights into that. And we did cover our coupling. We'll go ahead and do the attendance. Thank you very much for being here, for participating. Let's see, I'll go ahead and shut this off.